I'll invite our colleague who was mentioned already. And next topic will be digital twin for smart energy management. And we'll open the topic of AI for energy efficient industrial manufacturing. Tomáš Karásek from IT4I Innovation. Whether we split these topics or whether we combine them, will split because the questions will be different. So, okay, the first topic is the digital twin for smart energy management. So this is the topic of this presentation, and then we'll move on to industrial manufacturing. Mr. Tomáš Karásek.
Okay, so I will speak of digital twins. Our work package is split into two parts, as you have been informed, and we are here. A quick definition, what is a digital twin? So you have a reality, and then you have a model that is describing it, and it's a numerical model, and together it's called digital twin in order to understand it. So the data that we create, either with our calculation or analytic, and then the real data from measurements, then we put it into an AI network, and it comes up with the digital twin itself. And how do we approach it? And how do we process it? This is what I want to be talking about. What is the motivation behind it? So, with buildings, regardless of their use, the majority of energy of residential building is used for heating. That 62% is used for heating. Then for cooling, it's different. You see here cooling with some type of buildings makes also sense, but heating costs a lot, and the efficiency in energy management of the building is very important as energy prices continue to rise. So why do we deal with it? And what concept have we chosen? Our concept is based on an analytical model which is able to describe the building. So this model is simple, but there are several parameters that you need to consider. And you see on this picture that weather plays an important role, not only the temperatures, but also the sun. And of course, in case of clouds, or you will see what kind of role the weather plays. Then very important is wind. It's not the case where there is minus 10 degrees outside, but the felt temperature is even lower. No, here it does have an influence on the parameters that I will be talking about. And in the room, you can have different heat sources, you can have a computer, but also people inside. You might have noticed during the lunch, it got warmer and warmer in the room, and this is because there was maybe 700 people. People create heat, and if you calculate, it's like a boiler or heater that's heating the temperature in a room when you have it full of people.
Třeba počítat. Samozřejmě, pokud to bude nějaký pokoj s jedním člověkem, tak to nemá cenu řešit.
So in these kind of rooms, theaters, movie theaters, it's the 100 of watts that comes together, and the heat comfort is also an important issue that interests us. Next thing that we need to be aware of is that our building is not isolated somewhere on a hill or not surrounded by anything. And an important parameter is also shading. So AI created these pictures. So AI tools created this picture, and I quite liked it. But the sense here is the lower building is partially in the shadow, partially in the sun, and there can be huge differences. And then you need to consider it as well. You don't consider this building as being fully in the sun or fully in the shade, because the energy flow in the summer can be very varied and it can have an impact on our modeling. A few equations just to scare you off. So we are talking about these equations, about conduction of the heat. What we need to know are two basic parameters that are stated here. So we have a coefficient of the heat transfer, and then the alpha coefficient, which is being calculated. We need it, and this is the felt temperature, the temperature, how we feel it in the building. And this is the way how the heat is being transferred into the temperature of the wall. And of course, this is influenced also by the wind from outside. What other parameters enter this model? So we have the room dimensions, because this heat transfer and distribution of heat depends on the size of the room. Of course, the wall thickness is very important. The thicker the wall, you remember probably the old castles, which are very cold in the summer and even colder in the winter, so they have very thick walls. You need to know the outdoor temperature, the indoor temperature, and the heat transfer coefficient as well. So you need to know how the heat transfers between the air and the wall. Then you also need to know about the wall itself. So you need to know the parameters, you need to know what the wall is being produced of, and then also the reflectivity of the wall. So, for example, in 2024, there were floods in our area, and we had to renovate our home, and my wife was looking for the color of the outside facade. And of course, the color also is important, how it reflects the sun and the heat. And for example, gray, the color of gray means that the facade can be even 5 temperatures or 5 degrees warmer compared to other colors. So the reflectivity is also a very important parameter. Here, just to show off a little bit what we are dealing with. So we have a Newton method that we apply here, and we calculate the temperature. And in the room, our model works in a way that we turn on or turn off. Here is the large Q, which is heating, stands for heating, and we say yes, the temperature in the next step should be the temperature of the previous step plus other parameters added. Then it's a virtual thermometer, which is measuring, and if it's set to, for example, 21 degrees, it drops to 20 and a half and then turns on the heating. So it is a virtual heater and virtual thermometer that basically controls this whole solution I have been talking about. So our workflow looks like, how does it look like? So I have convinced my colleagues to be lean, and we try to have everything automated and automatic, and all these kind of steps or operations don't have to be repeated all the time. So thanks to our colleagues, we have chosen a blender. It is a very strong tool. So this is what we do. We take information about the building from OpenStreetMaps. You will see how. Then with the blender, we calculate the shadow or the shading, and then we take other information from the BIM model, and then again with the blender, we identify the rooms, and then we put everything into the model. And then the question was, where do we get the external data from? We take it from Meteo Data, external server, really nice information that it provides you with. You enter your parameters or coordinates, and it gives you everything you need. And it really contains everything, direction of the wind, temperature in 2 meters, and low, and so on. So yes, we are connected to this open database of metadata. How does it work after? So this is an automated system. Okay, so my colleague has entered the address of our university, and this is how we are able to semi-automatically calculate the shades and the shadows on this building. So she picks the building and then the surroundings. So this is now quite, this is for the users, and now you see the sun movement on one specific model. So for our model, it will be sufficient to have a look maybe from January 1 to December 31st, and we have a full shade map. We get it automatic. Everything thanks to this mentioned Blender and the script. So only intervention, user intervention, is the one I showed you right at the beginning. The next thing is, when we get the BIM models from our colleagues from the university, we need to split it into the several rooms, and we need to acquire the information about the specific rooms. So thanks to Blender and some algorithms, we are able to identify the rooms and enter those into our calculation model. So again, the colleague has shown now how we are able to identify the room and also the connecting rooms and the rooms under and above. This is a graphic algorithm showing you the interconnection we needed to be able to tell you that, yeah, okay, this room neighbors or is connected to the next room, and then also there is the outside next on the neighboring wall, and so on. So this is how it is split into the different rooms, surfaces, and we are able to get all the necessary information. Everything is fully automatic, so no user intervention is needed. And together with the colleagues we work on, we want to have the information fully automatic and that it will be automatically transferred into our calculation. The most important phase is testing phase, whether it really works. So we came up with, for the time being, it's not the simplest example. It's not a very simple house. It is 3 rooms. We want to test also that some of the rooms can also have a free roof. There are windows, different kind of interconnections, and we want to ensure that once the rooms overlap, that the correct data is being transferred. So this is a more sophisticated testing example. So once we will have a BIM model of a real building, we will use those for further testing. I will now show you 2 examples. One is boring, so I will wait for the end, but one is a bit more interesting. So here you can see the information that we have taken. I have given my colleague time period. It was beginning of February, a kind of a time frame. I picked my house. So I discovered it was minus 20 degrees Celsius in February. So the blue line shows you the temperatures, and the green shows you the sun, how the sun was shining, how many hours, and basically how long the sun was shining. Very important factor are clouds. So on the server where we get the data from, what they do is they have also the condition of the sky. Was it clear? Was it cloudy? It is also important. When you look at it, In August, you can have very high input, but if the weather is not nice, it's cloudy, then it's zero, basically, and it gives you false results then in this respect. So the power consumption. So, I mean, we really want to have a model which is as precise as possible. A standard heating, a standard condition is quite boring, I would tell you. And this is why I said to my colleague, like, Tom, okay, let's pick 10 days, or let's define 10 days. Here you start heating in a normal way, then I go for vacation for 6 days. I set my heater for vacation mode. So the temperature will drop to 17 degrees, but once I return, I want to have 21.5 degrees Celsius because my wife requires it. So please do the calculation. So this is the heat curve, and here you have an overview how the temperature in the room has changed. The green part, this is like the drops, ups and downs of the temperature, because the thermometer is trying to keep the temperature between 21 and 22. So once you set 21.5, there is a tolerance, or the temperature drops, and then it starts heating. So this is where we will still at home. So 21.5. Then at 7 o'clock in the morning, we got in the car and went skiing. And you see how the temperature dropped. So no heating. So there was zero, basically, or no heating. And once the temperature dropped to the lower limit, so 16.5, so the boiler or heater started heating and kept the temperature at 17 degrees, more or less. And on Friday, because we were supposed to return on Sunday morning, so already on a Friday it started to heat up in order to be in the condition once we arrive home on Sunday that the required 21.5 degrees will be achieved. So this is like a model situation. It is 240 kilowatt hours of consumption for heating. We compared it to the normal mode. So I go on vacation and I don't change anything. It will be 21.5 degrees. Nothing happens. So you see it's constant temperature, and then it is 267 kilowatt hours. So I save 10% only by kind of turning down the heating for those 5 days of vacation. Another thing happened, the white part you see here. This is not a mistake, it's an effect I will explain and describe on the next slide. This is the effect of the sunshine. Because you see, I mean, we have 3 beautiful windows on the house facing south. And on one day here, this day, on that day, the sun was shining really strongly, and it was clear sky, which meant, I mean, the heat went through the window and heated up, basically. It was a heat source. And then see 4 heating cycles turned off because the temperature dropped here slower and the sun maintained the required temperature in the room. 267 kilowatt hours is the mode without turning off for vacation. And then I said to myself, okay, Tom, please turn off the sun. So I will want to know what kind of effect does the sun have on it. So let's imagine it's February, no sun, and here the overall consumption rose to 284 kilowatt hours. You see, the sun does have an effect, even though it's in February. So you have to count with it. If I don't count with it, then the results will be different than I expected, or than I wanted. So this is an example that we have prepared for you to test our creations. And Now, with the colleagues from the Slovak Technological University, we are working on receiving the BIM model of a real building. Then we will kind of read the model, we take all the parameters, and we will be able to create this kind of energy information and balance information of this building. And once we get the data on consumption from the real building, we will compare it with the model consumption. Then we will be able to start dealing with identifying non-efficiencies. And we will then also be able to use those for smarter solutions or heating systems. And let me remind you of our ultimate goal is a so-called digital twin of the real building. And if we will have time, we would also like to go one step further. We would like to have the digital twin even more accurate, to use maybe different or other AI models and processes in order to be able to give the planners or the architects already kind of calculations that will help, for example, also with, I don't know, air conditioning and ventilation in rooms like that, because we want to have it already in the project and in the plan of the building plan. I think this is a very strong tool that could be used if we combine the options or possibilities of BIM with the possibilities that AI provides us with, and with our knowledge altogether, I think we can create a very interesting tool for the architects, for the planners, for, I don't know, for everybody who kind of designs, or for the designers that create the ventilations and heat circulation. So this is my input. No. Yeah, I am here. I'm all ready. I took the mic. Okay, so which means that the first topic is behind us, and let's continue with the round of questions. Let's start asking directly. We don't have to have a. Of course, you can ask through Slido, but in case you have any questions, let me approach you with the mic. So, are there any questions, ladies, gentlemen? Let's have a look at Slido.
No, vyzerá, že nie. To znamená...
So there are no questions, so you answered everything in your first presentation.